All right, welcome back to lecture 3 of Cubstart iOS. Today we're covering closures, data flow, and lists. Three things that we're going to completely change how you build Swift UI apps. By the end of this lecture, you will understand how to make your UI respond to user interactions, how to display dynamic data, and how Swift UI decides to animate things. So let's get right into it. Quick announcement before we start. Homework 2 soft deadline is due by yesterday 11:59 p.m. This Friday, and we do accept late work, so don't stress if you need extra time, but try to stay on track. Just make sure you submit all your works before by the end of the semester, so you get a pass grade. And homework 3 will be released Saturday night. If you have any questions about logistics, feel free to post on ad. And all right, let's move on. Here's what we're covering today. First, a quick SwiftUI recap from last lecture. Then we will talk about closures, what they are, and why Swift uses them everywhere. After that, we'll get into data flow, which is how your data actually connects to your UI. Then we'll cover for each list and sections for displaying collections of data. And finally, we'll talk about view identity, which is how SwiftUI decides whether two views are the same or different. Okay, let's start with the recap. A view defines a piece of UI. So this is the core idea from last lecture. So every single thing you see on screen in a Swift UI app, text, images, buttons is a view. And every custom screen you build is also a view. Views are the fundamental building blocks. And Apple gives us a bunch of built-in views to work with. Text, image, button, text field, shapes like a rounded rectangle and capsule, and many more. Think of these like Lego bricks. Apple hands you a set of basic pieces, and your job is to combine them into something more complex and useful. And how do we combine them? Through composition. We build complex views by nesting simpler views inside each other. The simplest case is just a single view, like a text. But when we want to place views side by side, we use an H stack, short for horizontal stack. It lines up its child's view horizontally left to right. And when we want to stack things vertically, we use a V stack. So you can nest stacks. So here we have two H stacks inside of V stack, giving us a grid-like layout. There is also a Z stack, which layers views on top of each other along with Z-axis like Photoshop layers. We covered that last time. Now, how do we customize a view's appearance and behavior? We use this thing called view modifiers. Here we have a text that says hello, so we change foreground style, color.blue to make it blue, and .bold to make it bold. Each modifier creates a new modified version of the view. So one important thing, the order of modifiers matters in some cases. For example, if you apply the padding first, then the background. The background color covers the padded area, but if you flip those, background first, then padding, the background only covers the text, but the padding around it stays transparent. So pay attention to the order. And remember, Swift UI is declarative. You tell Swift UI what you want the UI to look like, and when the data changes, Swift UI figures out how to update the screen for you. You don't manually tell it to redraw things. This is a key difference from imperative UI frameworks. And last lecture, Justin gives you guys a demo building a GitHub repo header view. We didn't finish the whole thing during the lecture, but feel free to click on the link in the lecture slide and play around with it, making sure you understand all the code, so it will be really helpful when you get to build your final project. One more tool I want to mention is the SF Symbols. It's a free macOS app from Apple that gives you thousands of built-in icons you can use directly in your apps. They're designed to look consistent with iOS, and they're customizable. You can change their weights, color, and even add animations. Download it from the link if you haven't already. It's super useful. All right, let's get into our first big topic, closures. So, what is a closure? A closure is a self-contained block of functionality, basically a chunk of code that you can pass around and use in your program. If you've taken CS61A, these are essentially lambdas. One of the special properties of closure is that they can capture and store references to variables and constants from surrounding context where they're defined. This is called closing over those variables. That's where the name closure comes from. Don't worry if that sounds abstract for now. We will look at concrete examples. There are three types of closures in Swift. First, global functions. These are the regular functions you've been writing. They don't capture any outside values. And second, nested functions. A function defines inside other functions. They have a name and can capture variables, capture values from their enclosing function. Third, closure expressions. These are unnamed, lightweight closures. Think of them as anonymous functions. This is the one you will see most often in Swift UI, and it's basically equivalent to a lambda in Python. So now let's talk about what capturing actually means with an example. Here we have a function called make incrementer. It takes an integer parameter called amount, and here's the interesting part. It returns a function. Look at the return type. It's parameter points to integer, which the empty parameter means it takes in nothing but returns an integer. And we inside make incrementer we have a variable called running total starting at 0 and a nested function called incrementer. The incrementer function adds amount to running total and returns the new value. Then make incrementer returns the incrementer function. So here's a key insight. The incrementer is a closure that captures references to both running total and amount. Even after make incrementer finishes executing and its local scope is gone, the incrementer function still holds onto those values. That's what capturing means. The closure retains access to variables from its surrounding context beyond their normal lifetime. So let's see it in action. We call make incrementer with amount 10 and store the result in increment by 10. Remember, increment by 10 is now a function. When we call increment by 10 with the parameter the first time, running total goes from 0 to 10, then it returns 10. Call again, goes from 10 to 20, returns 10, 20, again 30. So the closure remembers its state between calls. And if you create a second incrementer by calling make incrementer again, the new one gets its own separate running total. They don't interfere with each other. It's like each closure has its own private copy of the captured state. So now let's look at the most common way you will actually use closure in practice. Closure expressions. A great example is the sorted method. Sorted takes a closure that accepts two elements of the same type as the array and returns a bool. If the closure returns true, the first element should come before the second in the sorted result. If false, the second comes first. So for an array of string, the closure type should be string in the parameter and returns bool. So here's the straightforward approach. We have an array of names. We write a regular function called backward and takes two strings and return true if the first one is greater, meaning we want reverse alphabetical order. This works, but writing a whole separate function for something this simple is overkill. So we now Swift let us simplify this step by step. First, we can put it all in one line. It's short enough. Then, since Swift knows we are calling sorted on an array of strings, it can infer that S1 and S2 must be string, so we can drop the type annotations. So it's just S1, S2, return bool in returns S1 bigger than S2. So we can keep going. Swift knows a closure must return a bool. That's what sorted expects. So we can drop the return keyword since it's a single expression closure. So now S1, S2 in S1 bigger than S2, and we can go even further using shorthand argument names. Swift provides shorthand argument names for inline closures. So $0 infers to the first argument, $1 for the second, $2 for the third, and so on. So our closure becomes just $0 bigger than $1. That's it. We went from a multi-line function definition all the way to just $0 bigger than $1. So it reads naturally sort names where the first element should be bigger than the second one. This is the syntax you will see everywhere in Swift and Swift UI. So get comfortable with that. So great. We're done with closure. And okay, so let's talk about Dataflow. How your data connects to your UI in Swift UI. Here, we have a simple view with a button. We have a variable num tab starting at 0, and when the button is tapped, we want to increment it by 1. Seems straightforward, right? But when you try this in Xcode, you get an error. Left side of mutating operator is immutable. Self is immutable. What's going on? So here's the thing. Swift UI views are structs, and structs are value types. So by design, a struct's properties cannot be mutated from within its own methods. This is just how structs work in Swift. They're meant to be lightweight and immutable. Now we can't switch to classes because Swift UI is built around structs. Structs are lightweight, which allows Swift UI to recreate and compare views very efficiently. So we need another way to handle mutable states. So the solution is sState property wrapper. When you put sState in front of a variable declaration, you're telling Swift UI, hey, I need this variable to be mutable. I want you to manage its storage. What happens behind the scenes is that Swift UI moves that variable storage out of the struct and into a separate location that Swift UI controls. Now when the value changes, Swift UI knows about it, and it can announce, this value changed. Only views can depend on it need to re-render. And it's efficient. Swift UI only re-rendered the specific views that actually use that sState variable. Everything else stays untouched. So now let's make it more interesting. We add string interpolation to our button label, tap me. Now the button contents actually depend on numtab and initially shows tap me 0. When we tap the button, numtabs becomes 1. Swift UI detects the change and asks, are there any views that depend on numtabs? Yes. So our button text depends on it. So Swift UI tells that text to re-render with the new value. Now it shows tap me 1. This dependency relationship is the core of Swift UI's data flow. So tap again, numtabs becomes 2. The button re-renders to tap me 2, and so on. The key concept here is that as they create a source of truths, the single location that piece of data lives. Now, what if we want to extract our button to its own reusable view? We create a new struct called incrementable button and move the button code there. Then in content view, we just use incrementable button takes in numtabs, column numtabs, but there's a problem. Both content view and incrementable button have sState variable numtabs. That means Swift UI creates two separate pieces of storage, two independent variables. When you tap the button, only incrementable buttons numtabs change. So content view's numtab stays at 0. We've broken our single source of truth. So we need to fix it. So the way we are fixing it is using app binding. It's the child view. Incrementable button we changed as state to app binding. This tells SwiftUI, oh, I don't own this data. I'm borrowing from my parents. Then at the call state in content view, instead of passing num tabs, which would just pass an integer value of 0, we pass $sign num tabs. With a $sign access the binding version of the state variable. Now incrementable value. Now incrementable button can both read and write to content views num tabs. There's one source of truth in content view, and the child view has two-way connection to it. When you tap the button, it modifies content views num tabs, and everything stays in sync. So here's another example using text field. This is which is a built-in SwiftUI view for text input like a login field. We create a custom header text field view that takes a app binding variable text and a regular variable header. In content view, we have at state private variable text equals the quoting sign as the source of truth, and we pass $sign text down to the header text field, which passes it further down to SwiftUI's built-in text field. When the user types, text field writes back through the binding chain all the way up to content views text variable. The data flows down through bindings and writes flow back up. So this pattern of as state in the parent and at binding in the child is fundamental to SwiftUI. So now we know how data flows. Let's talk about displaying collections of data. Often you have a list of data like an array of student names and you want to create a view for each item. You can hardcode text views for each student, but that's static and doesn't scale. Instead, we use for each. You give it a collection and a closure that produces a view for each element. Here we loop over an array of strings and create a text for each student's name. One important requirement for each needs to uniquely identify each element. Here we use ID column backward slash dot self, which uses the string's own hash value as its identifier. We will talk more about identification options in a moment. So the cleanest approach is to conform your data type to the identifiable protocol. A protocol is contract. It says if you want to be identifiable, you must have an ID property with a unique value. Here our student struct conforms to identifiable by having a let ID equals UID parameter. So UID generates a universally unique identifier, basically a random string that's guaranteed to be unique. For those, if you're taking CS161, you've probably seen UIDs before. So when your struct conforms to identifiable, for each can automatically identify each element by its ID property. So you can just write for each student, taking students without specifying on an ID parameter. So for each associate each text view with its student's ID, which lets SwiftUI properly animate insertions, deletions, and reorderings. So here, student ID is unique for each student. So we write ID column backslash dot student ID. A key path is just a way to reference a specific property. The syntax is backslash dot property name. And the third option is when you use backslash dot self, so it computes the hash of the entire object and uses that as an identifier. So don't worry too much about the detail of hashing. If you've taken 61B, you will learn all about it. Just know that for simple types like strings, ID column backslash dot self works great. So in our original example with an array of strings, since string is hashable, we can use ID dot self, and Swift uses each string's hash value as its unique identifier. Now for each generates views, but doesn't give you scrolling or the native iOS listing styling. For that, use list. So list is a container that displays rows of data in a single scrollable column. It also supports selections and editing. The syntax is nearly identical to for each. You pass in your data, and a closure to create each row. But this gives you the familiar iOS table view look with separators and scroll behavior automatically. You can group rows into sections using section. Each section can have a header and contains its own for each. Here we have a favorite fruit section and a bad fruit section, each with their own data and header text. This is how you create group organized lists, like what you see in the iOS setting app. So last topic, we'll be go through view identity. This subtle but important for understanding how Swift UI animates things. Here's a question: if you have a red circle on one screen and a blue circle on the next screen, are they the same view or different views? And the answer determines how Swift UI animates the transition. So if Swift UI considers them the same view, it preserves the view and animates the change. So the red circle will smoothly move and transition into blue circle. Some view, same view, same identity, Swift UI just updates its property. So if Swift UI considers them different views, it destroys the old one and creates a new one. So red circle fades out and the blue circle fades in. Different views, different identities. Swift UI transitions between them independently. So there are two types of view identifier. The first is explicit identity. Explicit identity is when you assign a specific ID to a view, like the ID parameter in for each. Each view is associated with a data-driven identifier, like a dog tag ID in this rescue dogs example. Because Swift UI knows which view corresponds to which ID, it can automatically generate the right animations where data changes. So if a dog gets adopted and moves one section to another, Swift UI smoothly animates that transition because it can track the view by its ID. Like this. Okay, so the second type is structural identity. So with structural identity, Swift UI identifies views based on their type and position in the view hierarchy. The classic example is an if-else statement. Here, if user exists, we show login view. Otherwise, we show authentication view. So Swift UI treats these as two completely different views because they are in different branches of the conditional. When the condition changes, one view is destroyed and the other is created. Here's a more concrete example. We have as state variable show red. If show red is true, we show a red circle, and else we show a blue circle. When show red becomes false, Swift UI sees two different views in two different branches. So it fades out the red circle and fades in the blue circle. The views are destroyed and recreated. But if we rewrite this using a single circle with a operator in the fill modifier, show red question mark color dot red column color dot blue, now it's in one view. Swift UI sees the same circle in the same position. So when show red changes, it just updates view color. No fade in or out, just a smooth color change. The view is preserved. So to summarize view identity, when comparing two views across the screen states, ask whether they are the same or different. Same views get their states updated smoothly. Different views get destroyed and recreated with a transition. Explicit identity uses custom IDs, like in for each. Structural identity uses the views type and position, like if-else branches. So when possible, prefer the ternary operator approaches over if-else for changing view properties. It preserves view identity, which is more performant because Swift UI doesn't need to destroy and recreate views. Use if-else when you're actually showing completely different views, like login view versus authentication view. Okay, so let's wrap up with a summary. So today we went through closure, a self-contained blocks of functionality that capture variables from their surrounding context. There are lambdas in Python. You will use them with built-in functions like map, filter, sort, and extensively throughout Swift UI. At state and at binding. At state declares a source of truth for mutable data in the view. At binding creates a two-way connections so a child view can read and write to the parent's source of truth for each, for creating views dynamically from a collection of data. Each element needs to be identifiable. Lists and sections for displaying scrollable lists with group data, view identity. Explicit identity uses custom IDs. Structural identity uses position in the view hierarchy. Prefer ternary operators over if-else when you're just changing properties to preserve view identity and get better performance. So that's it for today. Homework 3 drops Saturday night. So see you all next week.